Hello and welcome back to my YouTube channel, my friends. In this video, you will be learning about the theory of computation, wherein we'll be covering all the topics that come under closure properties of context-free languages. Firstly, we need to know what are context-free languages. So here is the introduction to CFLs. CFL is a language generated by context-free grammar. So that is CFG. This CFG consists of variables, terminals, start symbols, and production rules. For example, the language of balanced parenthesis is also a context-free language. So the key features of these context-free languages are that it is useful in programming languages and their compilers. It is also represented using pushdown automata, that is PDA. What is a closure property? Understanding a closure property. Closure property refers to a set being closed under an operation. If applying an operation to elements in a set results in an element within the same set, then it satisfies the closure property. For CFLs, the closure property helps us understand which operations preserve the CFL status. So the operations considered for CFLs are here. The common ones are union, concatenation, clean star, intersection with regular languages, complementation, and the others including substitution and reversal. Closed under union. So the CFLs are closed under union, wherein the proof outline shows that for the L1 and L2 languages as CFLs, we need to construct a CFG, that is the context-free grammar. Here L1 is language 1 and L2 is another language. To create a new symbol with S, and we need to add a production. So when added a production, we get S gives S1 or S2, wherein we will be combining both the grammars of L1 and L2. Hence, CFLs are closed under union. We also have closure under concatenation. So CFLs are closed under concatenation. When trying to prove this, we need to let G1 and G2, that is grammar 1 and grammar 2, generate two different languages respectively, that is language 1 and language 2. However, the new CFG will be given with a production S gives S1 S2, wherein we will be combining the rules of G1 and G2. Hence we write it as just S1 and S2 together. Closure under the clean star. To prove that CFLs are closed under the clean star, we need to define a grammar G for the language L, wherein we will be adding a new start symbol S, and the production will be S gives epsilon or SS1, wherein epsilon is just the null string or the null symbol which shows that the context-free language has null inputs. So when we repeat these steps using recursive rules, we can prove that CFLs are closed under clean star. However, there are also non-closure properties for CFLs. So here are a few properties that CFLs are not closed in. So the first one is introduction, that is intersection in general. So the previous intersection which we saw was closed under CFLs since it was the intersection with regular languages R. So here we denote it as L intersection R. However, here under the non-closure properties, we have the intersection in general, that is the intersection of L1 and L2. These are not closed. We also have complementation, that is L. For example, we have L1 which is A power n and B power n, and L2 which is B power n and C power n. However, when combining these two under intersection, L1 intersection L2 will be A power n, B power n and C power n, which is not a CFL. When we look into the practical applications of the closure properties of CFL, here are the reasons why we should study CFL closure properties. So the first one is compiler design. However, it shows that the syntax checking of programming languages is being done using these closure properties. The second one is the parsing algorithms. The efficient language recognitions are being done using parsing algorithms, and these parsing algorithms use the logic of closure properties of CFLs. We also have formal language theory, wherein we understand the language transformations from one context-free language to another using these closure properties. That's all for today, my friends. I will come back with more such contents. Until then, thank you.